Okay, I'll admit gladly that I don't like to drive or cook or get groceries. I'm lazy. Sure, you can say that, but I know there are millions of you out there like me who would rather Uber than drive. Have you ever wondered how Uber platform scales for millions of concurrent users like us? They must get billions of database transactions a day. I am absolutely fascinated by how Uber designed its platform to handle those insane number of requests. So I invited Ankit Srivastava, senior staff engineer at Uber, to learn all about it. Stick around because this ride is going to be awesome. Hi Ankit, thanks for joining us on the show today.
Thank you for having me, Priyanka. Really glad to be here.
So, we all know what Uber is, but to kickstart our conversation, let's start with what powers that simple experience of clicking a button to get a ride or get food at our doorsteps.
Priyanka, the first time I used Uber, I fell in love with the simple experience where you could get a car at the tap of a button. It seemed magical. Being here at Uber for the past 6 years, and the pace at which Uber is evolving to become the essential for day-to-day consumer needs, I'm still learning all the intricacies of various product features that we have. At a very high level, when a consumer clicks on the Get a Ride or Get Food button, we capture the user's intent and fulfill it by matching it with the right set of providers nearby. Now, fulfillment models the user's intent as demand, and any active provider session that can fulfill this demand as supply in its systems. We in the fulfillment team at Uber develop platforms to orchestrate and manage the life cycle of ongoing orders, jobs, and providers across millions of active user sessions around the world. In essence, fulfillment is a foundational platform capability that powers existing lines of businesses and enables rapid scaling of new verticals seamlessly. The platform handles millions of concurrent user sessions and billions of trips per year across thousands of cities globally. We handle billions of database transactions every day. There are hundreds of microservices at Uber that rely on the platform as a source of truth for the accurate state of any ongoing order, job, or a driver and a delivery person's session. Now, the events that are generated by this platform, they're used by hundreds of offline datasets to take critical business decisions. 500 plus developers extend the platform using APIs, events, and code to build 120 plus unique fulfillment flows across various lines of businesses.
Wow. All right. So, this fulfillment platform, it sounds like this is the backbone of Uber's architecture. Now, let's say I ordered an Uber. How does the request flow work from the driver to the rider to this fulfillment platform?
When you open the Uber Rider app and request a ride, the request goes through a series of checks and validation, and it eventually triggers fulfillment to create a new order for the consumer. This order represents the intent of the consumer, and we translate the intent to individual jobs that need to be processed, and we store all of this information in Spanner. Now, these jobs are periodically read by our matching engine and offered to any open provider or supply nearby. Now, we used to store all of this data in our on-prem database, and we recently moved to Spanner.
Okay, so what were the challenges you were facing with this on-prem database in this original architecture?
We leveraged a NoSQL storage engine, Cassandra, to maintain the real-time state of all fulfillment entities on-prem. In order to maintain some notion of serializability, on top of Cassandra, we used StringPop to provide individual entity-level serialization. There were a few major challenges, but let me highlight a couple of them. Cassandra is built on the paradigm of eventual consistency. In addition to that, in a multi-data center setup, it's really hard to guarantee low latency quorum writes with Cassandra. As Uber's products and services evolved, we started seeing complex storage interactions that required multi-row and multi-table writes. So we had to build an application layer framework to orchestrate these operations by leveraging the Saga pattern. But the underlying storage platform with Cassandra being eventually consistent, it often led to inconsistencies that had to be manually corrected. What it translated in the real world would be a rider seeing two different drivers dispatched to them. So imagine you being out there near your office, and there are two drivers who arrive to pick you up. It's a bit confusing for anyone out there. As we scaled globally to millions of active users, even a notion of consistency became harder to achieve at our application layer. In addition to all of this, as we scaled, we started seeing horizontal scaling bottlenecks as well in the overall architecture. primarily because of the way we sharded with our application layer with Ringpop. This is when we started tracing our steps back to the properties of a traditional SQL based storage engine that provides asset guarantees. We started defining a transactional storage engine that would provide consistency as the primary capability. One of the things that has been in mainstream technology was NewSQL storage engines that combine the scalability of a NoSQL architecture with strong asset guarantees. This is when we came across Google Cloud Spanner.
Now, so that definitely sounds like, a lot of hit trials and then figuring out what's working and what's not working. Definitely the eventual consistency was not the aspect that could be lived with, especially with this scale. So what were the thought process and methodologies that you were exploring when transitioning from NoSQL to NewSQL?
When we were thinking about the next chapter for Uber's fulfillment platform, the focus on consistency became one of the primary evaluation criteria, along with high resiliency and availability. Based on our requirements and various benchmarks, we evaluated various NewSQL storage engines that were out there: CockroachDB, FoundationDB, and Cloud Spanner. Cloud Spanner provided all the functional requirements. It scaled horizontally with our benchmarks and provided us with a managed solution for cluster management and maintenance.
Now, how does the new fulfillment architecture with Spanner work? Can we dive into the architecture?
Yeah, we leverage Spanner's North America multi-region configuration as a storage engine for all fulfillment entities. Now, fulfillment service runs in Uber's own operational regions, which are in North America as well, and they make a sequence of network calls across to Spanner, which is deployed in Google Cloud for every transaction that a user makes. So every user request or any system operation, it results in a transaction against one or more rows and across one or more tables in Cloud Spanner. With Spanner, we are able to provide a consistent view of all our data to internal as well as external customers.
So it sounds like Uber leverages this hybrid of on-premise and cloud infrastructure. Now, knowing that keeping latency to the minimum is the biggest factor for an app like Uber, how do you set up the networking architecture that enabled that seamless and lowest latency interaction between this fulfillment application layer on-premise and then the cloud spanner, which is in Google Cloud?
Thanks to Uber's global networking infrastructure team and Google Cloud Platform's networking team, we have built an extremely resilient and highly reliable network infrastructure to support Uber's workload. In order to achieve this, we separated the networking infrastructure into two major components: the physical layer that consists of the interconnections between Uber and the cloud vendors, and a logical layer that consists of virtual connections on top of the physical layer to achieve redundancy. We built redundancy across these layers by having multiple routers and local access points at each physical network route, and an additional layer of redundancy with the logical connections on top. We even leverage Google's private Google Access to route all of Uber's traffic to Google APIs through the cloud interconnect VLAN attachments. This reduced the need of routing the traffic through public internet and provided additional reliability. To validate our architecture, the teams came up with a benchmarking suite that validates all the physical and logical network routes extensively. And we find any inefficiencies in the test setup very quickly. This was extremely critical for the success of the overall project.
Yeah, I can only imagine how connectivity and those benchmarking tests must have been so critical to make this happen. Now, you've been on Spanner for quite some time. How did the transition to Spanner help? What were the benefits?
Priyanka, building a specialized database is extremely complex, and maintaining or operating it is much harder. With consistency as the primary feature provided by Spanner, and it being a managed solution, we're able to leverage a ton of storage functionalities out of the box. This has given us time back to focus on building the domain of fulfillment and provide our customers with richer experiences.
So I cannot even imagine when you were migrating to Cloud Spanner, we were still ordering food and rides. How did the team make sure that the migration and switchover were seamless so the end users could have the same experience?
This was extremely tricky. One of the things that we agreed upon from the beginning was an internal platform re-architecture should not impact the consumers in any way. So we focused on building the technology that would seamlessly migrate any ongoing user session from our old architecture to the new spanner-based architecture. Now, since the data models and database topology of our old platform was significantly different from the new architecture that leveraged Spanner, any kind of live migration data was ruled out. Additionally, given the fact that most of this data is ephemeral and continuously changing every minute, doing a live migration through backups will only result in loss of data. So we built a system that intercepts a request from a user session and tags them to the world where the user session started. Now, if there are any ongoing orders for the session, we do not migrate the user session till the order is completed. For an open user session with no active orders, we switch them to the new architecture, which is backed by Spanner. Now, the team automated all of this through tooling, and we tested the tooling rigorously in our testing, staging, and shadow environments. We even set up test cities where we simulated hundreds of riders and drivers, their behavior in the real world to ensure we can observe the impact of this migration. Now, these migrations were done one city at a time, in some cases, batch of cities, and it took more than 6 months to complete. Now, spreading this migration over 6 months also helped us to continuously migrate business feature from the old stack to the new stack. There were 120 plus business features that were to be migrated from the old stack to the new stack. So the overall technical and execution perspective, it was a very difficult and challenging project that we undertook as a team.
You're literally changing like the tires of the car while the car is going. So I can totally imagine how those benchmarking tests and those tooling would have been a critical part of this entire migration. When you run planet scale architecture like this, and I don't use the word planet scale a lot, but here it aptly fits because this platform handles millions of concurrent users and billions of trips per month across over 10,000 cities, which translates to billions of database transactions a day. There is a lot happening. Optimizing and operating Spanner at that scale must be crucial because you need to keep the costs low and performance high. So let's bring in Pritam Shah, Engineering Director for Cloud Spanner, who helped Uber bring this architecture to life. Hi Pritam, so nice to have you. Walk us through the migration journey and the challenges that come with this scale of migration.
Thank you for having me. On the migration planning front, there are 5 things I can talk about in terms of challenges. First, how do we test at Uber scale? And how do we review the experience that a rider would have and the performance metrics so that we know we are ready? So designing and executing this test is a real challenge. Second is agreeing on migration first with acceptable performance, and then fine-tuning for better cost and performance optimization was another challenge. The third one would be capacity planning. So how do we right size and have the right amount of capacity in Spanner? The fourth one, which is one of the most critical ones, is how do we do this migration with zero downtime? So do a live migration with no disruption to Uber's business is quite a bit of challenge. And how do we do it in phases while keeping the lights on? And the fifth one is partnering with Uber to ensure that everyone is set up for success. So for example, after the migration is done, what kind of observability and introspection do we need in place? What kind of alerting do we need in place? The data protection strategy and the playbooks for incident management. The key was getting aligned on a common goal and agreeing where we want to be, by what time, and partnering closely with Uber in this journey.
You're really giving us truly behind the scenes look. Even I was curious to know what happens, what needs to be done to make this happen. Any business with Uber scale, obviously no pun intended, will truly benefit from just learning what these steps were. And it also underscores that this is possible to accomplish a migration of such scale and how to actually even get there. So Ankit, I want to ask you, what are some of the performance optimizations that were done to deliver this kind of user experience?
As Preetham mentioned, I think the more important part was during the migration phase, figuring out what is the right amount of observability we need across the board to ensure that we can find these kind of inefficiencies quickly and iterate on them. This operational rigor, giving attention to various dashboards, metrics, and diligence in evaluating every abnormality was extremely critical. So some of the performance optimizations that we worked on in collaboration across many teams were primarily focused on the networking stack. The two primary issues that we foresaw in the networking stack was around the TCP resets and the intermittent packet loss. By optimizing the gRPC channel pool, whenever a channel is affected by the TCP resets, the requests are automatically forwarded temporarily to a backup healthy gRPC channel. This allows for the request to be forwarded instantly without having to wait for a new spanner session. In a contained environment, we saw improvements of 1.7 times to 7 times, with an average 2.5 time reduction of errors. Similarly, another common cause of suboptimal availability guarantee is intermittent packet loss. Recovering from these conditions can sometimes be in order of minutes, further degrading the overall application performance. With frequent health checks, we can detect broken TCP connections within 5 seconds and initiate a graceful reconnect on broken gRPC channels. With these improvements, we were able to reduce the total number of errors by almost 4 times.
Wow, those networking improvements sounds like they were so critical to this whole setup. Now, Preetham, how do you optimize for cost when using Spanner at that scale?
Yeah, we did a few things to optimize for cost for Uber. So for example, we optimized node utilization. So in case of a multi-region configuration, a read can be issued to the leader or to the replica. If a strong read is issued to the replica, it incurs the extra cost of latency until the replica has the latest snapshot to serve the strong read. To reduce the impact on latency, we leveraged Google's private service connect and we routed the strong reads to the leader region and all the stale reads were routed to the replica only region. This helped us in maximizing the utilization of the nodes across the leader and the replica region. There are other cool things that Ankit and team have done on the latency and cost optimization.
Yeah, in addition to the private service connect, which optimizes how the traffic routing works across the leader and replica region, we also did an autoscaler and on-prem cache to improve the overall latency and cost. As you're aware that Uber's traffic pattern is variable by the time of day and week, being provisioned for maximum capacity at all time wastes resources. To take advantage of Cloud Spanner's elasticity, we built an autoscaler that constantly tunes the number of nodes based on a CPU utilization target. So as the traffic is variable, based on a constant CPU utilization target, we're able to achieve maximum elasticity out of the Cloud Spanner cluster. Similarly, most of our workload is very read heavy. So we built an on-prem cache to improve the latency and cost. To maintain the same consistency as Spanner, we only route the stale reads to Spanner, and we allow our cache to serve snapshot isolation based on Spanner's true time. We built a query caching functionality to serve just the stale reads from cache that is hydrated by strong reads and writes.
Wow, awesome. Okay, so what I heard is networking optimizations, caching, and also auto scaling. Well, awesome. Ankit, Preetham, thank you so much for sharing such a complex system design architecture and migration story with Cloud Spanner as a star. I am absolutely blown away seeing what it takes for my Uber ride to show up reliably.
It was absolutely a pleasure partnering with Uber on building the fulfillment platform, which is the backbone of Uber's architecture. And every time I take an Uber, I will get to tell my kids that the ride was powered by Spanner.
Thank you, Preetham. Thank you, Priyanka. It was awesome to be here and share our journey. With Spanner as a building block and a redesign of our application data models, we have truly laid the foundation for our next chapter, where we are working on scaling our platform infrastructure by almost 10 times and building and modeling many complex business features and verticals on top. We are truly on day one of this journey, and there's a lot to do and explore. We're hiring, come join us and be a part of it.
Well, now you know what it will take to scale and handle an application with millions of concurrent requests. It's not magic, it's Google Cloud Spanner and some planning. Did this help you? Let me know in the comments below. If you're curious about any other use cases, drop a note and I will do my best to bring that to you.